know what is emission, I'll explain you everything. Let me just write it. And the transition probability, so this is the then probability over pi to n. N is the, let's say, number of bins, total bins. Okay, emission probability of I and the transition probability from previous state to the present state. Okay, that's all we need to bother about. Now I'll explain you what is this. Okay, this is the same thing that we did here. Just think about it now. Take this example now. How do we actually calculate this probability? So let us first see that. So we need to calculate probability of observing no umbrella, followed by umbrella, no umbrella given that it is sunny, raining, sunny. This is what we need to. How do we calculate? We calculate in the following manner. We say probability of observing no umbrella, given that the state was sunny, right? This can be calculated, right? This is one of the emission probability. I'll tell you what do I mean by emission probability. Times. Why? Because we are looking at the sequence. Things are happening together. So it's a joint distribution, right? This, right? Times, according to Bayes' theorem, what is the probability of being in sunny state, right? Being in sunny state. This is sunny state. So this is the proper sunny, right? What is the probability of being in sunny state? So you might say that in the beginning, so this was the start of the model, right? This is the start of the model. This is the, so start can be anything, right? Could be cloudy or could be sunny, right? So generally we take this probability as 0.5 because you are starting your hidden Markov model at this stage. But the moment I say, what is the probability of transiting from sunny to cloudy? That has to be calculated. Times we go to the next one. What is the probability of being sunny given that the hidden state is cloudy, but cloudy has transited from sunny. So what is the probability of transition from sunny to cloudy? Okay, times what is the next one? Is no sunny. What is the probability of no sun? Sorry, no umbrella. Given that, what is the transition probability of from raining to sunny? Right? That's how we calculate this probability. It's the joint distribution of all the probabilities. That's all. Multiply all the probabilities that we have. Now let us see. Okay, I think there is a mistake over here. I didn't write it properly. Okay, let me rewrite. So just ignore this one for the time being. First part was correct. Probability of no umbrella given that it is sunny time, and probability of getting into sunny state, which is in the beginning is 0.5 because 0.5 for the raining state. And then next one is uh, umbrella, probability of observing umbrella given that I am in raining state. Okay, because right now we are in the raining state. Okay, times probability of transiting from sunny to raining because the previous one was sunny. Right? That's the correct way. This was the incorrect way. And likewise, the next one, probability of observing no sun given that it's sunny. And what is the probability of transiting from previous, which was raining, to sunny? That's how we calculate. This is the right way of calculating this probability. Okay. So you can already guess that this is your, all these are your transition probabilities from previous state to the present state. And this is the green ones that I will write is the emission probability. Okay, let's look at more formally. Do you have time? 5-10 minutes more, so that we finish this part, hidden Markov model, and then we will see in the next class what are the other ways of doing the same. Yes.
Yes.
Okay. So what we do is to understand the emission and the transition probabilities. Let us find out, let us see another component of within our flow model, which is how do we represent this? We represent this using state transition diagram. State transition diagram. And that is for the present example, we have two states. One is that we have some sunny state. So the hidden states are the part of the state transition diagram, and then you have cloudy state or raining. So what happens is that sunny may remain sunny, right? Let's say today is sunny, tomorrow it may remain sunny, and next day also it remains sunny. So then there will be some probability of sunny remains sunny, and likewise cloudy remains cloudy. Okay. But sometimes sunny is transiting to cloudy, and in other times cloudy is becoming sunny, right? That's what happens in this sequence that's given over here, right? That's what is happening here. Sunny remains sunny, sunny remains sunny, and sunny is becoming cloudy. Cloudy remains cloudy, cloudy remains cloudy, cloudy remains cloudy, cloudy becomes sunny remains sunny, and so on, right? So that's what we are condensing over here. So you have these transitions now, 4 different transitions. Probability by which it remains sunny to sunny is known as transition probability. So sunny to sunny remains, let's say, most of the time, 0.9 probability. Sometimes 0.1 to 0.1 probability it is transiting to raining state. Now, how do I know 0.9? These are arbitrary numbers, but you can get this through historical data. You can get the weather record of 1 year, and you can calculate this. What was the probability of sunny to transition, sunny to cloudy transition. You can get that data from AccuWeather, and you can get this analysis done. And let's say rainy remains rainy. So 0.8 probability, and rest of the probability is converting back to sunny. So these are transition probabilities. So these are your transition probability. That should be easy, right? And what is emission probability? Emission probability is also very easy to understand. Think of the following. What is the probability of seeing umbrella? Okay, given that it's the sunny state. Okay, this should be low. Let's say I am taking some arbitrary number. Let's say 0.3. Okay. What is the probability of seeing no umbrella? Given that it's sunny, this should be high. So I'm putting 0.7, right? Don't worry about these numbers. Just look at this. And likewise, you can have other variables. Let's say you are watching another thing. You are looking at the raincoat also, and let's say if you can see his feet is having some mud or having some wet clothes and so on. Those variables can also be counted, right? And likewise, you can have probability for this state, right? Probability of observing an umbrella given that is raining would be very high. Let's say 0.9, 0.99, let's say. Probability of having no umbrella given that it's raining should be low, 0.01. These are your emission probabilities. Okay, and what we are doing here is the same thing. See, this was your emission probability, right? No umbrella given that is sunny. That's the emission probability. This is emission probability of observing umbrella given that is cloudy, right? And look at transition now. Probability of probability of transition from sunny to rainy and rainy to sunny over here, right? So these are transition probabilities over here written in this form, right? These are transition and emission probabilities. What you do is you multiply all these probabilities, right, through this equation. And you understand why do we multiply? Because it's the joint distribution. There is a condition called AND, right? What is the probability of having an umbrella given that it's sunny? And what is the probability of being in sunny state, right? So you have to multiply. So now you can look at this equation. So this is nothing but what we wrote over here. but we are maximizing, which means that we are taking max of all probabilities, right? So this tells about the joint distribution, and that's what we did here. This is what we did. This is our joint distribution. This multiplication is represented with this symbol. Okay, and I is the sequence state. This is I. Let's say I is equal to 1 here, I is equal to 2 here, I is equal to 3 here. That's what it means. So when I say EI, emission probability at state I, this one, what is the probability of observing no umbrella given that it's sunny? That's what it is. TI, transition probability from previous to present. Previous was nothing, so start of the model, which means probability of entering into sunny state, which is generally 0.5 because there are two states, sunny or cloudy, 0.5, 0.5 to start with. But then after it has to be fixed. For example, sunny to sunny, we know is 0.9, right? Sunny to sunny is 0.9. We know this is over here. So that's how we calculate this. So you understand this equation. Now we know that we have seen the mathematical description of it. We know that we have to calculate these probabilities in this manner, right? However, we do not know that how do we calculate it quickly, because it's going to take time. It's going to be exhaustive search. Yeah, of course, somebody is writing whether the data will vary. It will vary, so you need to work with the robust data. Or sometimes what happens, you start with some probabilities, and then there are algorithms available to fine tune those probabilities to better ones, which gives you the better result. Okay, training that we call. However, if you, let's say, you take the whole genome data in a particular cell line, and that cell line is, let's say, any cell line, you trained your data on HeLa cell line, let's say, okay, and there were so many 200,000 bins for one chromosome, so many bins out there through which you learn transition probabilities and emission probabilities. Now you apply it to another cell line. It is unlikely to be incorrect probabilities, right? Genome has same way of functioning, same way in a sense the codes that we are talking about, the chromatin types, that's the fundamental thing in eukaryotes and mammalian genome. So that's not going to change. If there is a poised state having K27, K4 trimethylation, this is going to be true in all the cell lines wherever they are coming together. That's not going to change. So if you train your model, let's say you learn these probabilities from one cell line, you can certainly apply it to another one. The best would be you learn to multiple cell lines, right? Okay, so once we learn this, the question is, we know how to calculate these probabilities, right? We know how to calculate this. The problem is calculating so many probabilities over here, enormous probabilities over here, okay, would take so much of time and it becomes impractical. So how do we do this? So there is a smarter way available. What we do, we use Viterbi algorithm, okay, which solves our problem of so many computation. Now, talking about Viterbi algorithm, this is outside the scope of this course, but you will learn about this algorithm in Bio 4.1 because HMM is not restricted to chromatin types only. You have people also use it for gene prediction, coding and non-coding region. Coding is one state, non-coding is another state. You also use it for protein secondary structure prediction, where you have multiple state, alpha helical region, beta sheet region, loop region, and so on, 4 or 5 different states, right? So that can also be predicted in it. And so you will learn about the Viterbi algorithm, how does it work and why does it work in the Bio 4.1 course. But for the time being, you learn through this example that we can actually predict this hidden state. We can infer this hidden state from the observed one, right? To inverting the problem, to finding out what explains best the observation, what combination of hidden state explains the observed sequence. Okay, and that sequence has to be hidden over here, right? So we know this thing. Now consider that this observation was your histone modification, various description histone modifications, chromatin marks, you can say marks, and your hidden thing is your chromatin types. right? So that's what I showed over here. This is your hidden thing over here. This is your observed sequence, right? So if we get that, if we use HMM, we can get this. And this is known as from HMM. This model that we discussed when we apply it to chromatin is known as from HMM. Let me give you some example also. So you remember, instead of having umbrella and umbrella, you will have monomethylation, trimethylation of K4 acetylation, K36 trimethylation, DNACP demethylation in place of umbrella and umbrella. Now, this model was very, very simple. Look at the number of variables increased in when you apply chromatin. And the hidden state will be maybe 10, 11 states, red chromatin, green chromatin, yellow chromatin, whatever. Voice promoter, active promoter, strong enhancer, weak enhancer, transcribed region, electrochromatized one, polyform depressed one, repeat regions, and so on, right? But you, by taking this analogy of umbrella and umbrella and sunny, cloudy thing, you can understand that this can be applied to chromatin. Show you the example how it like there one of the authors. You see 10, 11 states on the right hand side. But it's the following. You have active promoter here, right? Which is the red state. And what you see, active promoter is having low level of monomethylation, but very high level of di and trimethylation and high level of acetylation. And weak promoter has everything is bit weaker. Acetylation is weaker over there, right? Look at the inactive and twice promoter. It has weaker signal over here, right? And then it has K27 trimethylation, K27 trimethylation. That's the twice one, okay? So these are frequency of those events. They have, it's like a emission probability thing, okay? Observed frequency, you can calculate this. Okay, strong enhancer. Look at all the marks, including, this is important, monomethylation enhancer thing that I taught you, right? Monomethylation is very high, along with relatively lower level of trimethylation. That's what I was telling you. It's high here, but it's relatively lower. It's high here, but it's low here, right? And of course, acetylation mark will be there at all the regulatory elements. And there's another class where all these values are slightly moderate as compared to this one. That's called strong enhancer. This is strong enhancer 1, this is strong enhancer 2. Not written here, but that's how they are described in the rest of the paper. Weak enhancer over here, weak or twice enhancer, is having less of acetylation mark, but more of monomethylation and dimethylation. And very weak one, this is also weak 1, weak 2, is having only monomethylation 1, right? Transcriptional elongation, K36 trimethylation is high, and K20 monomethylation, which I didn't speak about, is also high at the transcribed region. Transcriptional elongation only has, so this is transcribed one, transcriptional transition, that's different. Transcriptional transition is associated with cell line to cell line. Let's not talk about that right now. Transcriptional